Hi everyone, these are the questions people had just before the exam coming up. The first one was on 1C, and then there was some on 1D, 1E, as well as the review. That's what these ones are, the review. Some of them I'm going to say just cut because they were not what I intended them to be. And I'm sorry about that, but okay, let's go through 1C. All right. So this first one is on 1C, which is this one right here. It says, on a bumper car ride, friends smashed their cars into each other head-on, and each a speed change from 3 meters per second squared to 3.2 meters per second to 0 meters per second. The magnitudes of the acceleration of each car during the collision averaged 28 meters per second squared. So there's that acceleration. Determine the time interval needed to stop and the stopping distance for each car while colliding. So for each car, so they're saying each car does this. So I'm just going to say this is for one car. So one car is moving like this. It's got some initial velocity. It stops at the end. So we know there's going to be a displacement then that would look like this. And then in order to stop, there needed to be an acceleration pointing that way. So the first thing I'm going to do is find out the time. So I'm first going to find out the time interval needed to stop that distance, and I want to make a VO of that. So I know the initial velocity is 3.2 meters per second. I know the final velocity is 0, and they also told me the acceleration as well. So then I can use omega to find out what the, so I know the final velocity is 0. So I got now 0 equals V naught plus AT. I can subtract V naught from both sides, and V naught cancels out. So I got negative V naught equals AT. And then I divide both sides by A. And then I get negative V naught over A is equal to the time, and then I get, let's see, so it's negative 3.2 divided by my acceleration, which is 28, and then I get a time of, so calculating this out, negative 3.2 divided by 28, and I get 0.11, but negative 0.11 seconds, which basically means I made a mistake. And my mistake is that I forgot that the acceleration was negative, so that means that the acceleration is negative here. So so when I plug in a negative acceleration here, that then cancels out the negative, and so I do get a positive 0.11 seconds. All right, let's try this again now, but we want to find out what the stopping distance, so the displacement, that's what I'm looking for now, is the displacement. I'm going to use beta, and really I just need to plug in here. So this is going to be d equals my initial velocity, which is 3.2. I know the time now is 0.11 seconds plus 1/2 negative 28. And then the time, which is 0.11 squared. So let's go ahead and plug all that in. This time I'll use Desmos. Scientific calculator. So this is going to be, so 3.2 times 0.11, close parentheses, plus open parentheses here. So 1/2 is 0.5 times negative 28 times 0.11 squared. And there we go. So I get a displacement of 0.183. Or 18.3 centimeters, but I'll say 0.183 meters. So both mean the same thing. All right, moving right along. Next up, we got this one from the same practice assignment, which is 1C. This is number 11. It says a skateboarder is moving at a constant speed of 1.75 meters per second. When she starts up an incline, that causes her to slow down an acceleration of negative 0.2 meters per second squared. How much time passes when she begins to slow down until she begins to move back down the incline? So I'll draw the incline right here, something like that. So she's doing this up to here. So I know she's moving some initial velocity like this. And then when she goes to move back down, well, her final velocity then has to be 0, right? Because so she's moving up but slowing down, so she's going to then slow down, come to a stop, and go back down the other direction. So the other thing I know is that the acceleration points down the incline. And I think that's all I need to do. I guess I could also draw out the displacement, so I know that as well. And then let's go from here. So I'm going to write a VOVAT. So I know the final velocity is 0. Initial velocity is 1.75 meters per second. The acceleration is negative 0.2 meters per second squared. And I'm looking for the time. So I think I'm going to use omega. I know the final velocity is 0. And so I can solve for the time. I get v equals at. So dividing both sides by a, that gives me v over a is my time. So again, my initial velocity is 1.75. My acceleration is, what did I do? Because again, I screwed up the, whoops, my final velocity is 0. My mistake. So let's try that again. So final velocity is 0, so this is 0 equals v naught plus at. Subtract v naught from both sides. Goes away on the right side, so I get negative v naught equals at. Lastly, divide both sides by a. That goes away, and I get negative v naught over a is equal to the time. So it's going to be negative 1.75 divided by the acceleration, which is negative 0.2. And so I get a time of, and I'll plug this into my other calculator. Looks like I got 8.75, so 8.75 seconds. And there's that one. All right. So now moving on to this one, 1D, was a question of 6, which is, it says, the airplane in the figure below, so let's move this down a little bit. Airplane in the figure below starts from rest and accelerates 3 meters per second squared for 30 seconds before leaving the ground. What's the plane's displacement? Well, all right, so they already give me a diagram, so that's nice. So I'm going to make a VOVAT. I know the plane starts at rest, so that's 0. I know that the acceleration is 3 meters per second squared, and I know this happens for 30 seconds. So how do I get the displacement? Well, I think I'm going to use beta. Let's see if this gets me the displacement. So D equals, again, it starts from rest, so this term goes to 0. So this is going to be 1/2 times the acceleration, which is 3, times 30 squared. So my displacement then is 30 squared multiplied by 3 times 1/2. And I get 1350. And that seems reasonable. So there you go. There's part A. For part B then, So what are they asking for? How fast is the plane going when it took off? I think in this case I'm going to use omega. So I got now the final velocity, the initial velocity is 0, is equal to the acceleration times the time. The acceleration is 3, the time is 30. So this gives me a velocity of, I think 90. Yeah, 90. So 90 meters per second. And there's part B. All right, moving right along. Now we're going to part E here. Multi-parter here. This is all on free fall. So it says you accidentally drop an eraser out of a window in an apartment 15 meters above the ground. How long will the eraser, I don't know why it's capitalized, will it take for the eraser to reach the ground? Well, I'm going to draw a diagram. So here's the window building in the ground. And then we're dropping an eraser. So it's going to go right here just before it hits the ground. So at first the initial velocity is 0. Then it's going to have some velocity at the end that I don't know. However, I also know there's going to be some displacement. Oops. There's going to be some displacement, so I'll draw that like this. Here's my displacement. And then I know the acceleration, this is free fall, so it's going to point down like that. So I'll do parts A, B, and C all here. So here's part A. I'm going to make a VOVAT, because it's asking how long will it take to reach the ground. Well, let's see. I know this is a free fall problem, so the acceleration has to be negative 10 meters per second squared. I'm dropping it, so the initial velocity has to be 0. And they told me it takes 15 meters to reach the ground. So remember, though, that goes down, so that displacement is going to be negative 15 meters. All right, now I should be able to solve. So this is going to be D equals V naught T plus 1/2 AT squared. The initial velocity, though, is 0, so this term all goes to 0. So I get then my displacement is 1/2 AT squared. I'm solving for the time. So let's see. Let's plug in numbers here. So I'm going to have negative 15 equals 1/2 times negative 10 t squared. So this gives me negative 15 equals negative 5 t squared. The negatives cancel out. And then I divide both sides by 5. So the 5's cancel out, and 15 divided by 5 is 3. So lastly, I'm going to take the square root of both sides, and I get that t is equal to the square root of 3. And the square root of 3, if I plug it into my calculator, is 1.73 seconds. So there's the time. Let's bring this down here. Probably going to have to bring it down a little more. Beep, there we go. All right, so part C says, what speed will the interval have just before it reaches the ground? Well, that's then me trying to find out what this is. So in that case, for part B, I'm going to say, I'm going to use omega. And with this one, I'll say V equals the initial velocity. Well, it starts from rest, so that's just 0. And then the acceleration is negative 10 times the time, which is, I just found, which is 1.73. So the final velocity then is going to be negative 17.3 meters per second. All right, so lastly, we got part C. I'll do over here. Is if you multiply the time interval answer from A and the speed answer B, why is the result much more than 15 meters? So what they're saying here is if you multiply the time interval, the time, multiplied by the speed, how come you don't just get the displacement? And the reason is that this basically means the average velocity. Right? However, this object is accelerating. This object, so this is for the average velocity. So what, you know, the question basically is why can't I just use like unit cancellations? Meters per second times seconds gives me meters, so that should give me the distance. How come it's much more than that? And the reason is that it's actually getting faster as it goes down. This object is starting slow and then getting faster and faster and faster until it, you know, until it reaches something like this. So it's getting faster and faster and faster until it finally reaches the ground. So the velocity, this final velocity times the time, doesn't equal. Is not the same. The average velocity is not the same thing as these instantaneous velocities. All right, moving along here. So the other question was on 4, I believe, from part A as well. And my answer to this is do not do it. I'm sorry. We're going to do this at a later time, later in the semester. And I thought I cut all these types of problems out. I apparently did not. I apologize. Please don't worry about part 4 until next semester. And that applies as well for part 7 here of the review. So again, I apologize. Part 7 of the review, don't do. That's something we're going to figure out how to do next semester. Or this semester at the end of the semester. So sorry about that. All right. So next up here it says, to pass another car, Argo accelerated from 25 meters per second to 40 meters per second in 4 seconds. What's the acceleration? So again, what I got here is a car that's doing from here to here. Starts at rest, so I can say the initial velocity is 0. Then it's got some final velocity. So that must mean then the acceleration points in the positive direction. And there's also going to be a positive displacement as well. So to find out the acceleration, well, I could use one of my kinematic equations, but I'm also going to say that I'm going to use the definition of acceleration, which is the change in velocity over the change in time. So that then gives me that the acceleration, the average acceleration, is the final velocity minus the initial velocity. So it's a final velocity, that's the initial velocity, divided by the change in time, which is 4 seconds. And I get 40 minus 25 divided by 4. And that gives me 3.75. So this is 3.75 meters per second squared. And there you go. There's my acceleration. So again, skipping number 7. I apologize for even having it. So number 8 is a lot like the airball lab that you guys did. You threw the ball up in the air, right? And this is exactly kind of the same thing. So I'm going to make a diagram. So here's you throwing the ball up in the air. So here's my ball. It's going to go up to here. Sorry, I should say, it says Justin threw a basketball straight up into the air. He let go of the ball 3 meters above the ground. The ball was timed at 13 seconds before it reached its highest point. So it says make a diagram, label it, and make a volvat. So I'll diagram this. So let's see, it's going to have some initial velocity, final velocity. It's going to be 0. We know the displacement of the ball would be something like this, but it was also dropped at some initial height, which was 3 meters at that point. It's a free fall problem, so we know the acceleration has got to be down at -10. We'll talk more about that when I do my volvat. I think that's good with a diagram. So next up now is a volvat. So I write out all my knowns and unknowns. Let's see. At the peak, it's at rest, so I know that the final velocity is going to be 0. It's a free fall problem, so I know the acceleration is going to be -10 meters per second squared. And I also know that it does this for 13 seconds, because that's how much it was timed for. And that should be good right there. So there you go. There's my labeled diagram in volvat. Then it says, what's the initial velocity of the basketball just after Justin released the ball? Well, I can use omega. I know the final velocity is 0. So 0 equals v naught plus at. Subtract v naught from both sides. V naught cancels. And I get negative V naught equals AT. So lastly, I'm going to divide both sides by A. That gives me negative V naught over A is equal to my time. So negative V naught, that's negative, whoops. Whoops-a-daisy. Sorry, I'm trying to find V naught. Screwed that up. So it's this would be a little bit easier though. So all I need to do is subtract AT from both sides. So this now gives me negative AT is equal to V naught. So negative, the acceleration is negative 10. The time it took was 13 seconds. So that's the initial velocity. Negatives cancel out. And I get 130 meters per second, which is quite the arm. little silly, this scenario, but yeah, so that's the final velocity. And there you go. There's the solutions to those problems. Sorry about those ones that were issues that we'll do later in the semester, but I hope that helped. All right, take care. Bye.